Okay, welcome for today's first presentation. Ditcher is not present so far, so we start like it is. First talk is by Pierre Roybeau. I said it wrong, or?
No, that's right.
Okay, great. And we will hear about the automatic reconstruction of X-ray sense with Python and Data Lab. So let's start.
Good morning, everyone, and thank you for having me. So today I will talk about a real-world case study, how to use Data Lab for accelerating scientific algorithm development with a real case. So Data Lab can be an interactive companion to help you with your data algorithms and produce your result that you expect. So to begin with, a few words about myself. Initially, I trained as an optical engineer, and I hold a PhD in optics and photonics. So, but it was a long time ago. I began my career in research, and before moving into industrial R&D, and then scientific and industrial software. So now I work at Codra. I'm executive VP of Codra. Codra is a French software company. It's an SME with 200 employees today. In parallel of my professional activities, I've been involved in the open source community for a long time too, for almost 20 years now. I've created a bunch of projects. Some of them you might even know. The older ones may know about Python XY. It was the first all-in-one scientific Python distribution for Windows. Then I created Spider, the first ready-to-use scientific Python IDE for all platforms, actually. Then WinPython, which we replaced Python XY. Python XY is discontinued now. So WinPython, which was the first portable scientific Python distribution for Windows. And 3 years ago, I created Data Lab. Not the first one, but at least a scientific data processing platform that we will talk about now. So what is Data Lab? Data Lab is an open source platform for processing and visualizing 1D signals and 2D images. So it has more than 200 integrated processing features, which is quite a lot. It is built on Python, of course, and scientific libraries such as NumPy, SciPy, scikit-image, OpenCV, PlotPyStack, which is a visualization stack for building quickly signal and image processing software. And Sigma, the logo is bigger than the other one because Sigma is not, it's a dependency, an external dependency, but it was extracted from Data Lab last summer. It's actually the processing engine of Data Lab. But you may use that as a library, as a processing library, completely independently from Data Lab. The project was funded by CEA, our main client, which is represented today by Mark, which is right here. The NLNet Foundation, more recently, since last year, and Codra. So Data Lab, in a few words, it was meant to be ergonomic, interoperable, extensible, and robust. Actually, the first use case of Data Lab was the data processing for the Laser Megajoule facility, which is a huge laser facility in France, which is operated by CEA. So Data Lab is already in production there. And actually, it was designed the same way as we design Codra. We designed the control software of the facility. So when there was a need to process data, we designed Data Lab with the same requirements, the same robust requirements. So it is really an industrial grade software. It can be extended with Python scripts as plugins or macros. Macros live inside the workspace, and plugins extend with a new menu, new features. And it can be remote control thanks to a high-level API. We will see about it. So data lab may be used in various fields, as you may imagine, like data processing software, so research, industry, and education, but I will skip this part. To focus on the use cases, I always divide the use cases in 4 categories. The first one is analysis. So you may use data lab as a standalone application to process your data. So you may explore data, visualize data, and use one of the 200 integrated processing features. So it's just easy to prototype, to fine-tune your algorithms with data lab with a standalone application. It's quicker than writing your script or notebook, because you just select a processing feature, you change parameters, you see the result immediately. So it's very quick to iterate your algorithm details. So that's the first use case. The second one is prototyping. You may, because actually there are a lot of integrated features, but of course you have your own algorithms, your own code that you want to reuse. So you may connect remotely connect to data lab using your favorite IDE. So of course Spider, but to be honest, every other IDE as well, to connect to data lab and to reuse your algorithms together with the integrated features. So you may send data to data lab, trigger some process features remotely, and get back results in your IDE. You can do the exact same thing from your Jupyter notebook as well. The third use case is advanced debugging. You may use, again, the remote control feature of data lab to connect data lab to your own application and debug your application. So we will see about that, because that's today's topic, the example right here, the Xgrid application. And the fourth use case is integration. You may simply embed data lab in your own application to process data. Here is an example of control software on the Lazemegju facility. You have a control software from a huge diagnostic composed of several scientific cameras, motors, and digitizers, and so on. And here you can see, you can't see because it's too small, but there are small buttons that may be used to open data lab, send data to data lab, process data, and get back the results in the main software. So in this talk, we will focus on 2 use cases. The first one, analysis, and the second one, advanced debugging, with the Xgrid application, which is the topic of today, so the automatic reconstruction of large X-ray scenes. So what is Xgrid? No, before that, why Xgrid? So the motivation. So our client, the CEA, the need of the CEA is to be able to reconstruct a full field image of a scene. So why reconstruct it? Because actually the need is to be able to radiograph large objects, so typically 1 to 2 meters wide. They need to be able to do so mainly outdoors, but actually anywhere. So it has to be a field deployable acquisition. So they would use mobile X-ray equipment, either imaging plates or digital detector. Typically, the dimensions are there, so 35 centimeters by 43 centimeters. So it's quite small comparing to the object, but it's a limit of the technology. So the consequence is that the full scene cannot be captured in a single shot. So you need to reconstruct the complete radiography scene from individual shots. And that's why we have specified and developed Xgrid application for CEA to do it, and to do it fully automatically, as we will see. So here is the typical experimental setup. you see that we use an X-ray generator. There is the object, so the unknown object, which is quite large. Here something that we will talk about in a few seconds. Here you have the detectors. So in this example, this is an assembly of imaging plates, but so each individual imaging plate may be digitized using a portable imaging plate scanner. Then you obtain individual images and you have to reconstruct the full field image. It also can be an movable detector that you will use to do different acquisition positions and different shots, and you obtain same kind of matrix of sub-images that you need to reconstruct afterwards. And how would we be able to reconstruct the full scene image? Well, it's thanks to this grid here, which is composed of patterns that are made of metallic balls. And because metallic balls are either absorbing or scattering X-ray, that would be visible on the radiograph. So the idea is to use a grid that is composed of multiple patterns that are distributed across the grid at known position. So each pattern is unique, unique code, which is composed with the absence of presence of metallic balls. And so there is a code associated to each pattern. And so when you do the radiograph, you will have the object that you are seeing, the object that you are radiographing, and the patterns. And so by detecting and decoding the patterns, you will be able to reconstruct the full scene image to put back the image together. So why this is not standard image stitching? Actually, X-ray images are not like outdoor photographs. They are projections along the axis of radiography. So it means that when you see objects that are at the same place in the image, it doesn't mean that they are in the same place in the object. They may be in different plane along the radiography axis. And there are also difficulties, like the fact that radiographies are have generally low contrast, high noise, so no natural textual continuity, and no reliable acquisition metadata, because the whole experimental setup is outdoor in the field, so you can't rely on acquisition metadata to reconstruct the full field image. So this is not a panorama problem. You can't simply use a ready-to-use algorithm that is used to stitch your photographs on a panorama, and it requires a specific reconstruction approach. So, as we saw, the coded grid makes the reconstruction possible. Now, the software that we have implemented has two main challenges. The first one is to go from the individual sub-images to the whole full field image, fully following different steps of processing. We first will have to detect and decode the patterns, then estimate the homography, which is a mathematical transform to go from the detector plane to the grid plane. And we will then correct the images, the geometrical transform of the images, and assemble the full field scene. And the second challenge is that we need to do it fully automatically. So the end user has to be able to press a button and obtain the full field image. So no manual positioning of the individual images, no operator tuning, and no prior knowledge of the scene. So this is where Kodra developed XGrid and where Data Lab became essential. So about XGrid application. XGrid is a Python desktop application which relies on Qt for modern user interfaces, on several open source processing libraries like scikit-image, OpenCV or SciPy. And it also relies on plot-PyStack libraries for efficient 2D visualization. So that is quite important because we need to be able to zoom in, zoom out on the full field scene quite smoothly with the mouse. And to do so, we can't use slow libraries. So we had to use our own library, which is plotpy, which thanks to a Python C++ extension allows to do it very smoothly with large images, because we have the individual images maybe about 8,000 pixels by 7,000 pixels, so quite big, and we have on the full assembly something like 4 to 8 sub images, so it can be quite large scene. And of course, we use the data for prototyping and advanced debugging, as we will see now. So let's focus on the two use cases I was referring to earlier. So the first one is analysis. So how Data Lab helped us designing the processing pipeline. So the first step of the processing pipeline was pre-processing and denoising. We have to prepare the individual sub-images for the next step, which is the pattern detection and decoding. So it's not a simple denoising algorithm because it has to be adapted to all situations. Remember, we have to do it fully automatically. So to do so, we had to experiment on various data. So that's when that's what Data Lab made possible. We actually the final algorithm is composed of a combination of all those functions from scikit-image and SciPy, which are used with different parameters depending on the noise of the sub-images or the contrast of the sub-images. So it was really made possible because with Data Lab it's easy to fine-tune the algorithm. The results speaks for itself. So the second step is to detect coded patterns and to decode them. So we use the noise sub-image, and we use some algorithm to detect the metallic balls that you see here. So blob detection algorithm, and then some specific algorithm to understand what is the pattern and decode it. So again, Data Lab made this possible, relying on the OpenCV blob detector algorithm. Actually, we tested a lot of other blob detecting methods in scikit-image, for example, DOH, DOG, for those of you who know those kind of methods. The third step was homography estimation. So now that we have the denoise sub-images, the patterns, so we can estimate the transform to go from the detector plane to the grid plane and reconstruct the image. So we have to establish the connection between the patterns that we have detected and the known positions of the pattern in the grid plane. So that is the homography transform that we compute using OpenCV fine homography. So again, Data Lab made this possible. And the final step is the geometric correction. So we apply the homography transform to the image, and we do the image fusion. So again, Data Lab made this possible using warp perspective function from OpenCV. So here you have the full field scene, which has been reconstructed using individual images. You see that there are individual corrections which are different from one sub-image to another. So demo time, just to illustrate how it works in XGrid. So I will show you an example which is quite simple actually. So I open Xgrid. Oh, sorry. It's the fact that I use an animated GIF, so it began too quickly. Let's see it again. So I created a project. I'm selecting the sub-images. I remove every parameter, so it's fully automatic. And the pattern has been detected here on the left of the application. And the homography transform will be computed. And the whole scene is reconstructed on the right of the screen. So here it's a simple example. The contrast is quite good, actually. There's not much noise, so it's not really a huge challenge to do so automatically, but it's just to illustrate the principle. So the second use case I wanted to talk to you about is advanced debugging, because now that we have implemented the first algorithm, if it's not good enough, it's not optimized, and if it's not yet automatic, we may need to use advanced debugging. So in a classical debugger, you may explore your data when you at each stop of the code, at each breakpoint, you may explore the current stacks, variables, and so on. But for image processing, it may not be good enough, because you want to visualize data and to be able to process it or to change some algorithm parameters just to see if it works better than your original algorithm. So that's why we use Data Lab to connect to the Xgrid application. It allows us to visualize intermediate images and to test new methods. For example, to select a region of interest that are different from the original algorithm or different processing parameters. I'm sorry, what? Okay, 5 minutes. Okay, but we begin with yeah. Okay. Okay, so here is the demo of the advanced debugging, and it's my favorite part. So it would be it's very essential. So it's quite easy to do to implement the remote debugging. Actually, it's you only have to use a proxy that is provided by CGMA, the computing engine library of Data Lab, that also provide this remote control client. And you may use it in your application. And once you have connected to Data Lab here, it's quite easy to send images, intermediate images, or annotations, or anything you want to show on Data Lab. So labels with intermediate results and so on. So here is a demo. I'm launching Xgrid, another example with a radiograph with a little bit more noise. So only 4 of them. So I'm launching the algorithm just to show you the reconstruction. So here it is with the patterns. Now I will put the window away just to connect to Data Lab. So I'm launching the debug with Data Lab features. So I'm launching the clients. Now I'm launching the server, so Data Lab itself. It's connecting to Xgrid. It's connected. And I'm relaunching the algorithms just to see how it works. So it will send real-time the intermediate images, annotations, labels. So you see exactly how the algorithm works. So it defines region of interest. It's denoising images. It's finding the metallic balls you see here. And it's testing a lot of different possibilities before converging and obtaining the final results. So here you have the what you may see if you had a breakpoint. You can process all those individual images and test other techniques as you may want to optimize the algorithm. So takeaways. First one, we saw that a scientific pattern can solve demanding industrial imaging problems for demanding clients. 2, the fact that Data Lab accelerates algorithm design by with interactive experimentation and helping fine-tuning parameters of your algorithm. And 3rd, it creates a bridge between interactive exploration and the production application by using the remote control capabilities of Data Lab. So with Data Lab, you may see your algorithm, understanding, improve it. And it's not my marketing department who wrote this, but it could have been. All right, that's almost done. Just a quick word about a new project of ours. We have re-implemented Data Lab, full web re-implementation in the browser. So you may even test it in your browser. It's fully local, still local first philosophy. So no backend, no upload. And it opens new possibilities. So we are really grateful to NLNet Foundation for funding this new project. It's already available. But that's another story. Thank you.
Thank you very much for the talk. Do we have any questions? Okay.
For the amount of ball patterns that you need per mosaic for correct reconstruction, how many do you need? Because I've seen that on each tile that you basically have, you have multiple of those. So like 4 patterns, 5 patterns, or how many do you require to create a correct reconstruction?
Yes, that's a very good question. Actually, we need, if you have only one image, you need at least 3 patterns. But to compute the homography transform, but actually here we have more than one subimage, so we can use the fact that we know that one subimage is, for example, at the left of another subimage. So use the patterns of the other subimage as additional patterns. So in some situation, we may compute the transform with only one pattern on the subimage.
Okay, any more questions? If not, you can ask presenter directly. Let's thank Pierre once again. And
thank you.
Now we will be moving to the room 138.
Hello, hello. One. Okay. 1, 2, 3. Okay. Hi, everyone. So this is a change in the schedule because our first speaker didn't appear, and we wanted to give him time to actually appear. And Diego has fortunately agreed to hop in. So big thanks to Diego. Big applause, please. And I think we can start.
Hello, good morning everyone, and thanks for joining. So today I'm talking about why boring AI works and when BERT beats billion parameter model. So my talk today will wrap up a production use case relating to NLP. And for those ones that don't know what is BERT, so BERT model was created and open sourced by Google. And it was the model that kind of paved the road for large language models. So BERT actually enabled the transition from bag of words and TF-IDF. So we went from frequency of words in a large corpus of data to semantic meaning and representation in textual data. So BERT actually using parameters and transformers architecture enables to have this relation of sequence of words that come after one of the other, and it basically allows to have this semantic representation. So BERT has around 110,000 parameters. And the large version of BERT has 340,000 parameters compared to Claude and OpenAI models that are on the billion-sized parameters. So simply putting parameters is what allows these models to catch up the patterns in the textual corpus of the training data. So generally, the more parameters you have, more patterns you can learn from your training data. So I'm Diogo. I'm a data science lead at MDPI. I have over 8 years of experience, designing and deploying AI-powered solutions in the areas of NLP and computer vision. And MDPI is a publishing company, so we publish scientific articles. MDPI is based in Basel, Switzerland. So for almost any NLP task today, there is an easy solution, which is prompt and LLM, right? We can need classification inputs, we can have word tagging inputs or summarization. We have a very easy solution that we can rely, and it actually works. So it's not easy, doesn't kind of work sometimes. No, it does work. We can just, prompt an LLM and get reasonable questions and build demos rather fast. But however, this comes with a cost impact on the businesses, and they have, they generally absorb this cost without actually seeing the proportional value of what this adds to the companies. So my talk is about trying to explore, are we just solving the business problems or are we just reaching for the trendiest tool available? And to enlighten a bit on this question, there is this very simple case study, and it's very standard, right? We basically, it's a categorization problem. It's, categorizing inputs is very standard to any industry. And what we are doing here is categorizing scientific manuscripts. And for that, we have a BERT model that assigns these categories to every submitted manuscript based on the title and abstract. And we are using title and abstract because it's a short part of the manuscript that already enables us to capture the meaning of the entire manuscript. And also, one big disclaimer about why we are kind of restricted to title and abstract is because these BERT models that they only enable us to input of up to 512 tokens, and that's about roughly 400 to 450 words. So it's pretty much what the size of a title and abstract of a manuscript would look like. So we do have a well-defined task with standard inputs and a clear evaluation criteria. And during this task, we try to assign up to 3 categories per paper, and we have basically 12 high-level groups of categories. And what we are actually allowing the model to predict is 289 different categories. So the task is constrained, and it's what we are trying to define is a closed and well-defined classification problem. And by closed, I mean that there is a fixed number of labels that we are trying to assign to these articles. So there is a stable taxonomy. It's not that large. We are not, open-ending this classification and allowing to be open-ended. It's a fixed number of labels. We have a standardized input. So we are using, as I said, title and abstract. And title and abstract across manuscripts, they always have like similar sizes. There is a clear evaluation because it's a classification model. We can use pretty standard and objective evaluation metrics like precision and recall. So, assessing and comparing different approaches is very objective and very metric-driven, let's say, result. And we can run this at a very large volume, or the intention is to run this at a very large volume. So the solution is, or one of the solutions is a fine-tuned BERT multi-classifier, and it's a very, very simple architecture. So we have a title and abstract, we pass it to a BERT model with a multi-classification add, and we ranked it up to 3 different categories. So today, with the amount of GPU and computation power, putting this in production is very easy, is very cheap. It's small enough, it's fast enough, it can consume high volumes of data. It's very simple to fine-tune, and we can fine-tune it as the taxonomy evolves. And here, taxonomy evolves, it's not that we are enlarging or changing our target labels, it's more about what, for example, AI and machine learning represented 15 or 20 years ago is different than what means these fields 10 years ago and what it means these fields today. So, for example, software categories or software-related categories evolve at a different pace than, let's say, arts or ancient studies relating categories or social sciences related categories. Those kind of categories probably have a lower fast pace changing on what their means or what they represent, right? So what we use to evaluate and to assess and compare all of these approaches is actually we interacted with our authors. So the authors were actually validating the categories by themselves, and those are the people that are best positioned to judge what their articles is about, right? So they are the experts on the topic they wrote, so they know what their articles is about. So if you ever published before, you know that during the publishing process, there is a proofreading phase, and it's generally the interaction between the editors and the authors, and editors make suggestions to normal formatting or English editing, and the author needs to revalidate that. So during this phase, we would ask the authors if they wanted to voluntarily refine the categories or check them for us. So we had a very simple front end that the authors would be able to change their categories. So you can see it's here the front end that we used, and the authors would be able to see the title of their manuscripts. They would be able to here on the left side to navigate through these 12 high-level categories and then select or open this right drop-down list with the categories that belong to these ones, and they would be able to just say, all right, I don't agree with the suggested, so I can remove them, or I can add new ones, or I can just simply accept the ones that are suggested. So there are two constraints or notions that I need to point out here is, even though we only add 289 categories, it could take a few minutes for the authors to actually understand all of the categories that we have available in this taxonomy. And even though we had these two levels, they would need to first select the higher level, and this would be agriculture, clinical sciences, engineering, social sciences, agriculture already said it. So you could more or less say, all right, I think the category that I'm seeking is within this higher field, but it might not be as direct as an objective as they think. So navigating it, actually going through all the categories, it's not as easy, but we were kind of limited to this. What I'm trying to say is that when the authors were suggesting or replacing the categories, there might be some biases towards our initially suggested categories. And secondly, we notices after a few feedback from authors that we had some even misleading taxonomy within our categorization. We would have there would room for ambiguous duplicated labels that we had. So it's something that we are working on to try to improve that. But overall, in the end, we ended up with over 120,000 author-validated category decisions. So we had over 120 manuscripts with author-validated categories for those manuscripts. So during that, what we did was to compare a BERT model with GPT 4.1 and GPT 5.1. So the BERT classifier we used here was actually not the initial BERT classifier that we used to suggest the first AI suggested categories to the authors. It was like a second version of it. And obviously, among those 120 inputs, we used some in the data training, and we basically reserve a big chunk for this evaluation and comparison to other models. So again, we fine-tuned a BERT classifier, and then for the GPT models, we prompted with a few short learning, which means inside of the prompt, we had some examples on, all right, if you get this title and abstract, this is what the categories you would be assigned. So we tried to give as much context as possible. So what does it look like when we try to compare these three approaches? As I said, because we had this objective evaluation metrics, we could, have precision recall for these three models. And you can see that here BERT models are more precise. So it means that when they assign a category to the manuscript, that's more times the equivalent to what the author said. And because all articles are many times multi-scope, or they scope across multiple categories, that's what the recall is capturing, is are we selecting all the categories that we should? And even there, the BERT model is better than the GPT models. Anyway, even if we basically said, all right, all of the three models are identically performant, and if we take that, assumption, I think that here is where the case is really won for these, smaller models. It's in production environments in industry where you need to have, lower latency, reduced complexity, easier maintainability, and, you don't have extra charges or costs. The BERT model, so compared in, per million, the cost of per million times that we need to process. And for example, if we were to process the entire MDPI number of articles, I think we have over 2 million articles. So we would need to spend for per million for the GPT-0.4, we would need to spend $830 and for the GPT 5.1, 480. Here, I'm assuming that for running BERT, we spend $0, right? So we have our own service, so I'm not accounting for those costs relating to running a BERT. And how do these compare to in terms of medium processing time? So BERT is 16 times faster than GPT 4.1, and it's 40 times faster than GPT 5.1. And it can process a higher volume of bulk processing inputs. The reason is this large is because we need to give all of every time we want to infer with GPT models, we need to pass the entire context, right? We need to pass the instructions on what the model needs to do. We need to pass the entire list of categories. So it's a very, very large context window that we need to give to the models for them to understand, a very simple classification task. So this is not an anti-LLM talk by any means. So don't say, oh, that's the dude that doesn't like LLMs. That's not true. So even inside of this project, very simple project, we used LLMs, right? But we didn't use LLMs during the deployment and production phase. We used LLMs for multiple parts before even training the model and after for assessing whether the model was up to the standards. So first of all, data augmentation, because MDPI or the industry overall is producing more papers in some fields rather than others. We tried to generate some data, some synthetic data to balance a bit the training set. Also for labeling support, so we would validate and explore the training data set using LLMs to try to find some gaps and potentially misleading or debatable categorization assigned to our manuscripts, and also for the error analysis, right? So every time we basically train a new model, we could run the LLM and try to understand why we are having such misclassifications and when the model was assigning some categories that the author didn't have or the other way around. So we had some loops here. So we use the LLMs to try to improve actually the model. So LLMs are very, very powerful at the development phase. And the question is more whether these kind of approaches or models should be used for production inference for a very well-defined task. So my takeaways from this is that if you have a very specific task, you should use a smaller model, right? And this says if you have a well-defined label space, if you have standardized and predictable inputs, clear measurable assessment criteria, and if you want to process a very large volume of data. And in the other way around, if you have an open-ended problem, or if your requirements are always shifting, you can favor an LLM to solve your problem. So again, this is not an anti-LLM talk at all. I'm just kind of defining, or my point of view is that well-defined problems deserve simplest and reliable technology, and one that works, maintained, and it's scalable. So prompting LLM shouldn't excuse us from assessing other options and deploying the most reliable tool in production. And that's all. And sometimes the most impactful solution is the boring one. Thank you, everyone.
Thank you. Do we have questions? Yeah.
Thank you so much for your talk, Diogo. I would like to ask if you guys sound around and if you have some metrics about the accuracy of BERT at the end of this 220,000 evaluations or validations. Do you have some metrics on that? Thank you.
You mean these metrics, or what kind of metrics are you?
That was the metrics for the...
Yeah, okay. Yeah, exactly. Probably it's not, might not look as fancy as, you probably see in some other articles. But I think that the main reason here is that the taxonomy we are using might leave room for undecisiveness. And I think that the taxonomy we are using was targeted for MDPI scope. There is room for ambiguity. And for example, as a real example, we have a category called oncology, sorry. So oncology, but we also have lung cancer, prostate cancer, and a couple more different cancers. So there is ambiguity here, right? So it's basically the reason that it's like that is because MDPI publishes a lot in these specific types of cancer. And then we also need to have another category that would cover the other type of cancers. So there is some room for ambiguity even inside the taxonomy, which, if the author just accepted oncology as the category, and then this new model say, oh no, it's lung cancer, it's not oncology. It's not really wrong, but in these metrics, we are assigning it as wrong.
Okay, any other questions?
Hi, thank you for the talk. You were talking about using an LLM to do augmentation. How does that work exactly? Do you take an existing article and do you tell the LLM, please reformulate it completely so that it appears as a new article? Or do you take some categories and say, invent something completely new from these categories? Is there a standard way to do it?
So I think the first one, right? So the idea was you would pass some articles or one article and you would try to rewrite without really changing the content. So it means that you would have, let's say, different ways to say the same thing, and you would basically assign the same categories to that content. So the idea was to increase the representation of that category within the training set.
Okay, cool, thank you.
Okay, I think we still have time for one question. If there is none from the room, then I have one question. So you are using BERT. You are using BERT for categorization, right? So as far as I understand, the BERT is actually doing the embedding, right? So what was the connection between the embeddings and categories?
So it's BERT is doing the embedding, that's true, but then on top of that you have like a very simple classification ad that you put on top of that embedding, and then the model itself makes the classification for you.
Okay, so additional layer.
Yeah, exactly.
Okay, thank you. Thanks, Diego. Big round of applause. And we will not be having another talk since the speaker didn't come. So you are free to take a longer coffee break or join others in the other room.